Right, well, thank you all for joining us at another in our Value in Energy Data series of webinars. Today's webinar is focused on AI applications in the energy sector, generative AI and other forms of AI. So we have John Farland, who's the Director of Solutions Engineering for H2O AI, who's going to talk to us about some of the work that they've been doing in this space. So over to you, John. And whilst he's getting his slides up, please do put questions in the chat as we go. We will have time for Q&A at the end, and I'll kind of launch questions at him. If you have, if you have questions, put them in the chat and we'll handle them at the end.
Sounds good. Can you hear me okay, Sam or anybody?
Yep. Yeah,
cool.
Nice and clear. Pretty
classic moment of trying to get off mute there at the last second. So let me go into slideshow mode. Yeah, so, thanks for the opportunity to come talk about this. This is a very fascinating kind of topic. So what I'm going to talk about a little bit is generative AI, as well as some kind of more classic, I guess you'd call it now, concepts in machine learning, feature evolution, AutoML, and just like simply ML ops and deploying models, but all kind of applied to use cases in the energy industry. Just really quickly, my background is in energy. I work at H2O currently, and I'll describe what H2O is in just a second. But, I spent a long time working in consulting. I worked at ISO New England and a few other places in the energy industry. So my background's in energy, and I just love kind of now applying some of these really fascinating advanced analytics techniques to use cases in the energy industry. All right, so it's just a little bit of background about me. And then on the H2O side, you may or may not be familiar with H2O. H2O is a company that's been around for more than a decade now, I guess 12 years. And so we're not the new kids on the block. And like I said, I've only worked at H2O for the last few years, 2 to 3 years, but I've really used H2O in almost every job I've had over the last decade, at least, right? H2O's got a really advanced open source package that really made us kind of dominant, about a decade ago, right? And so because of that, we have a pretty big community, right? So we've got customers in 8 of the top 10 banks, and I'm realizing now this is very much focused on the United States, so sorry about that. But 8 of the top 10 banks in the States, 7 of the top 10 insurance companies, 4 of the top 10 manufacturing companies, and a lot of energy organizations that we'll kind of look through as well. Another thing to kind of think through is we've got a really deep data science bench. I believe we have the most Kaggle grandmasters on our data science team in the world, including I think 4 or 5 of the top 10, even the world's #1, Philip Singer. So just a little bit about H2O. We are a machine learning company, and I'll show and demo some stuff and talk a little about it. But we love applying these sorts of things to energy use cases, right? So if you are familiar with H2O, you're probably familiar with this slide, but just, whoever's not, just as a quick show and tell of like what H2O kind of is. H2O is a fundamental open source scalable library, the open source version of it, right? So whether you're coding in R or Python or with a GUI, that sort of thing, you can leverage really advanced and distributed algorithms to train models, right? So kind of back in the day, even on the open source side, we were kind of one of the first companies to go out there and create AutoML, for example. So you see this function call here. It's really just AutoML trying to train a model, right? And back in 2017, we came out with a much more, I would say, advanced product, which I'll show today, called driverless AI, which lends itself to these concepts of feature evolution and using genetic algorithms, right? And I'll demo that as well. Another thing you may or may not be familiar with, and everything I'm showing right now is completely open source, so I definitely encourage folks to go play around and try it out with any data that you might have. In addition to like AutoML and scalable machine learning, we kind of spent a lot of time focusing on explainable AI, right? So you might be familiar with Shapley values, right? So on the left, we kind of have like a pretty graphic of a bunch of features and variables that are going into a model and distributions of those Shapley values. So how much they contribute marginally to a given prediction globally across the data set. But I always think it's really fascinating is on the other side, when you also look very, very locally. So even row by row in a tabular set, what the Shapley contributions are. And we will also take a look at that as well. So that's just kind of a really quick introduction to H2O. I don't want to spend too much time pontificating about H2O and how awesome I think we are. But more to the point, right? So in the energy industry, we're really blessed to have access to a ton of data, right? So whether it be smart metering data, SCADA data, weather data, just tons of data. Documents is something I'm going to talk a little bit about that you probably haven't thought about as data per se, but definitely in the world of generative AI now, it is data, right? And so the point of this slide is to really say, the energy transition continues to happen all around the world. We are transitioning to prosumer model, right, where there's a lot of people generating and demanding energy, and how we kind of handle all that in a holistic way continues to be challenging, right? I work and have worked with a lot of utility companies, kind of regulators, energy commission, that sort of thing. And so what I've found challenging is that everybody's kind of at a different stage with digital maturity and AI governance and understanding, especially now with generative AI. What does this mean? How do I use it? Are there risks? Right? Those sorts of things, kind of a mixed bag in my experience with utilities and organizations. In addition to that, there's like a fractured and diverse landscape of legislation, right? So if you go one jurisdiction to another, one country to another, the rules change, right? And in the States, at least, we have system operators, and I think, in Europe, RTOs, right, that kind of facilitate the market. And each one of those has market regulations and rules. And so, that's actually a use case for generative AI that I'll show in a little bit on how you can quickly uh, understand those rules because they are so different place to place. And then finally, I mean, we all probably are aware of this if you're attending this webinar, right? Balancing the act between maintaining the grid and all these emerging technologies that are coming out, right? This is going to be challenging, and I believe it's only going to get more challenging, right? As we have more and more distributed energy resources, utility scale renewables and storage that come onto the grid. It's very challenging for grid operators to kind of maintain that balancing act there, right? So lots of challenges. And just real quickly, this slide definitely applies not only to the folks I've worked with in energy, but just generally speaking, we see a lot of this since we created a slide about this, where at the bottom you kind of see the typical flow where you might be interested in doing a pilot, or there's a use case driving you to use machine learning and AI, generative AI, right? But oftentimes the point of this slide is you want to get to the evolve and really adoption, right, of the technology in your business or organization. But too often you're just stuck in the proof of concept factory, as it's called, right? So you're stuck in this pilot phase, and there's vendors all over the place, and you're not quite sure even what success looks like, maybe, right? So we see that a lot, and I have seen that a lot for quite a long time. So putting it a little bit more specifically, we created this slide as an example, right, of what that might look like. So if you're a data scientist, right, maybe you get told to work on a project, right, and especially if you're like me, the first thing you do is start playing around with a notebook, right, and try to explore whatever data sets you have, maybe build some toy models, yada yada. That's kind of like the de facto approach, is to start working on a notebook. But then you might get to a good point, right? You might get a good model, and then you got to think about, like, well, how do I actually use this? How do I put this into production, right? And that's where the whole ML ops conversation comes in. Maybe that works, maybe that doesn't. And then you get to step 4, and the business user or the stakeholders of these models, they might not have any technical background or any idea what you did with the model, even if it did get into production. And ultimately, at the end of the day, I think the point is, like, too often we find ourselves in this situation where it just doesn't get used, and it's a complete waste of time. And that's kind of where that POC factory concept comes from. Oh, and by the way, that took 9 months to get to. I've just seen that constantly, right? And so what I'm going to show today is kind of what we have tried to do. And we've tried to get to this type of model for our customers, right? So we go from 9 months, hopefully, to something like 2 weeks, where you're a data scientist or a business analyst or, a DevOps kind of person. It doesn't really matter too much your background. We want to provide the tools that enable you to fail fast or just simply go quickly through this process, right? So we have a bunch of no-code AutoML tools I'll show that utilities have been using quite a bit. That gets a model going, just clicking a button and getting a model going. It doesn't need to be the final model, right? So as a data scientist, I resisted AutoML for a long time. right? But it doesn't need to be the final model. The point is you click a button and you get a pretty good benchmark very quickly, and you get a lot of understanding quickly to iterate on, right? Step three, you should be enabled to explain that model to a business owner, a non-technical person, right? ML ops. This is something that, I would say for the last 5 to 10 years, organizations have really struggled with. How do we apply AI governance and deploy these models so that they're usable for downstream applications, whether it be solar production forecasting, customer segmentation, load forecasting, right? There should be a common framework for deploying that sort of thing. And finally, how do people use this? How do non-technical people at my organization use this, right? And so especially now with generative AI, there's a lot of ways to create AI applications or AI use cases that folks can consume the predictions from a model, right? And the point is, all of that should really be a 2-week process if you can get that going, right? So those are the challenges, and that's kind of what I've seen be challenging in the energy industry, but there's massive opportunities, right? So we have, like I said in the beginning, we have tons of data, tons and tons of historical time series data. And just think of all the documents that utilities and regulators have now, right? Where there's tons of information stored in there for decades, right? That now with generative AI and some of these advanced NLP models, we can extract that data and use it and turn it into more traditional predictive models, right? I also think there's a lot of opportunity for automation, AI-based automation, to kind of facilitate some of the pain points, in the industry, like when organizations interact with each other, physical optimizations, right, like on the grid and grid ties, that sort of thing. And then also simple personal assistants. And I'll show one of these today where we've been working on, where this concept of like prompt to forecast, where you can simply say, hey, AI, go build me a predictive model that forecasts this county or zip code energy usage for the next 14 days. And it's able to go out there and it knows the sorts of APIs to go out there and build that model and at least get you a result. And literally you just prompted it to do it, right? That I think is kind of going to be a game changer. And then also just simply improving the balance of renewables and storage, right? So it's a very complex problem, but we do have some really advanced tools now to kind of help us there. So there's a lot of opportunity. Now we just kind of take a deep dive into what that looks like specifically, right? So what I've seen is just ubiquitous, is something like this sort of phased approach where when you're doing a machine learning project or you have a use case, whether it be generative AI or not, it kind of looks like this, right? So you state your desired business outcome. What are you trying to achieve? And be very clear about that. Phase two, no surprise here, go start building models, right? And we want to be able to build the best models as quick as we can, just to understand, we want to start with the state of the art if we can, right? And then we kind of go from there to see if we can improve upon that. And that's the fun stuff for people like me. But the reality is then we have to kind of monitor that and deploy that, right? It's very important to be able to take these models and make them useful. And so phase three is on the model deployment. Phase four is on the AI application that can actually go out there and get predictions from the deployed model and retrain the model if it has to. That's where that human in the loop type of feedback mechanism comes in. Right. So, okay, let's look at some fun stuff. So, it's kind of comical now. I guess we call it traditional machine learning or just predictive modeling as opposed to generative AI. But some really quick examples of this. Again, I bet a lot of this isn't too surprising to the folks on the phone. Load forecasting with renewables or distributed energy resources with PV and battery. This is kind of not the best graphic in the world, right? But this is kind of a low voltage example where you have battery discharging that you have to be able to predict, solar generation that you have to be able to predict, right? And all of that has to be augmented to your load forecast. So that red line is kind of like your load forecast. You need to adjust it. That's a complicated problem. That's an example of supervised learning from a traditional machine learning perspective. But there's also examples I've worked on a lot with unsupervised learning. So this is, kind of a pretty graphic that shows some clustering approaches, right? But in this case, what we're trying to do is take meter-based energy data, smart meter data, tie it up with weather, and try to understand who's the most susceptible or sensitive, right, to weather, and then kind of cluster them, and also add some behavioral aspects and really try to understand, is there a behavioral segmentation we can get out of that? And all of that's really an unsupervised example. Now, back in the day, deep learning was the coolest thing, right? So computer vision is one example of that. What I'm showing here is a model I built. EPRI here in the States released 8,000 high definition labeled drone images of high voltage transmission power lines, and that's kind of what we're seeing here. And happy to share the link to this open source data set that they share, because it's really incredible to play around with. And what I was able to do is kind of use one of our frameworks to build a really advanced model, very, very accurate model very quickly. It took me under an hour to train this really advanced neural network. As you can see on the left, just in the top left, this is an example of the truth. So this is kind of what the labeled data looks like. And then on the right, this is kind of what the model predicted. And as you kind of go through here, sure, the model's going to have challenges when the image quality is pretty poor, but it does a really good job. And quite literally, I built this in about an hour and was able to deploy it in about 4 or 5 minutes. Right. So that's the sort of thing that we're seeing with utilities, that they have the data. We have the data now. Right. And now the ability to quickly iterate and build models and understand what works and what doesn't. That's really important. So to tie out this kind of little segment on traditional machine learning, these are sorts of the use cases. And what I do is I try to map these use cases that I'm familiar with in the energy industry over to, buckets, machine learning categories, right? And so a lot of these are supervised problems, whether it be like propensity to adopt emerging technologies as a classification problem, regression problems, you're trying to predict, day ahead, maybe demand response, expected demand response reductions or energy efficiency. Very, very classic load and price forecasting. We've been doing that for 100 years, maybe, right? But now some of the more advanced stuff where we do have high frequency time series data, we might want to do anomaly detection, right? That's kind of another unsupervised example. We talked about meter segmentation as unsupervised. One salient example I just shared with computer vision is transmission and distribution predictive maintenance. On a predictive maintenance perspective, first you have to identify what's in the image first before you can tell if something's wrong with what's in the image, right? And this is one that we'll look at really quickly is now on the document stuff, now on like the text data, work order analysis. And when utilities have to ship a truck, right, or roll a truck as they call it, it costs them quite a bit of money to send a crew out to do something. And sometimes it's a waste of money, right? So really taking those work orders and the text and the notes from that and learning from that is one example, even from traditional machine learning that we can apply. But now, about a year ago, OpenAI came out with GPT-4 and put a chatbot on top of it. We got ChatGPT, and all we've really been talking about is generative AI for the last year and maybe year and 3 months. So, everyone's probably familiar with ChatGPT, but just really quickly, we've been working on developing a lot of training courses actually at H2O with generative AI, and we have a few public resources I can share where it really goes end to end with everything to do with generative AI. Not necessarily applied to an energy use case, but it's just kind of really simple, straightforward, end to end generative AI. And I took this slide from that training just describing, again, the little bit of a difference, defining the difference between a traditional AI model where you take data and labels, and maybe you have to do that labeling, but you have a very clear understanding of what you're trying to predict. And you get a predictive model to hopefully spit that out. Generative AI is a little different, right? So oftentimes it's unstructured data. It's just documents, and they could be of any different type or variety. And we have to take that and ingest that information and normally use a pre-trained model to output novel content and generate something. And we'll look at that in a second. I might skip this just in the sake of time. Obviously, it's a pretty heavy slide. If you're not familiar with the paper, attention is all you need. I definitely suggest checking it out. This slide is describing the transformer architecture, which has really just been transformational, right, in terms of our ability to handle text data, right, especially with generative AI. It has an encoder and a decoder part, right, and there's a lot of nuances in there, positional encoding, right. There's a lot of stuff going on here, but I wanted to have a slide on this just to say all these large language models, including GPT-4, the vast majority of them are using this kind of framework. And it's important to understand how this works in terms of limitations, token size, that sort of thing. There are, of course, other frameworks coming out. Mamba, you might have heard about, right? But that's really important to know that. This slide is really important. I just want to say, everyone I've talked to in the last year, this has kind of been an aha moment, and I know it's a little busy for what it's worth, but it's a good one to check out. And so if you just bear with me for a few seconds, if we kind of follow the flow of this diagram, in the top, well, middle top left, we're ingesting a data source. So for example,
Heal.
Oh, someone want to go on a mute there? Like I was saying, so if you have a document like an annual report from a company, right? And simply put, you want to be able to either converse with it or fine tune a large language model on top of it, or many versions of that. What we can do is take that document and index it, right? So we need to figure out a way to first, take all the text data out of it. So we're OCRing, object character recognition text out of it. We're turning it into chunks, right? And how we do that chunking strategy matters, but typically we've seen a sweet spot with about a kilobyte each chunk, right, of text data. We turn that text into a vector, right? So now I've got all these vectors, numerical representations of text data, and we store that in a vector database. So now we started from a document, and now we've got a bunch of vectors in a vector database, right? That's great. That's like the data processing piece. That's the ingestion piece. But then you come along at step 2 and you say, I've got a question. I want to be able to get information out of this document. And you start conversing with your data sources, right? So one example question might be, what is the current goodwill balance of Wells Fargo? Well, we take that text string, effectively, we turn that into a vector called the retrieval vector. And then using something like cosine similarity, we can compare this vector to all the other vectors in the vector database, return the top K. In this case, in this graphic, it's just the top 2. It could be top 5, top 10. Most similar vectors. So the most relevant pieces of text data from this document. And then we say, hey, large language model, given the following 2 chunks of text as context, what is the current goodwill balance of Wells Fargo? So we're grounding our question to very specific and relevant pieces of text data. And in this way, we're able to really ground the results and reduce the model from hallucinating and just making stuff up. It's extremely effective. And if you've kind of been in the space, you probably are aware of RAG. But I do think it's kind of mission critical to kind of understand this. So I just wanted to walk through that real quick, and I'll kind of demo that in a second. One really important part of generative AI now, if I flip back for a second, I kind of breezed over the fact we turn these chunks into vectors. I didn't really talk about how we actually do that. That's effectively embedding, right? So we're creating these embeddings of text data, and how we do that matters. How we take text strings and turn them into vectors, there's all different ways of doing that, and they all kind of have pros and cons, right? But just as a quick example of what that might look like, if you have a question like how many people live in Berlin, and these are all the possible candidate text strings, the most similar in this case might be the answer to the question. About 3.5 million people live in Berlin. In this way, we're trying to find the closest distance, the most similar vectors, most relevant piece of information to send to the large language model. And we'll look at that. All right, to kind of close this part out, what about the use cases in energy for generative AI? Well, there are a lot, right? So this is just a small subset where utilities are always very interested in customer satisfaction, for example, right? So voice of the customer. I already talked about work order optimization, conversational fraud detection. This is fascinating. We work with a lot of telecoms here in the States and abroad. And just when you're chatting with somebody, understanding if it's a bad actor, right? Now we have the ability to kind of do that using these advanced reasoning from large language models. We'll look at entity extraction, right? So if you have household bills or just paper data and you want to turn it into tabular data, digital data, you can do that very easily now with LLMs and RAGs. Document Q&A, just being able to converse with your internal knowledge base. We'll look at a quick example of compliance and market regulations, right? So if you're in a system operator or a market, trying to understand rules around that. And yeah, behavioral program implementation. I mean, we're able to kind of have these AI assistants really understand usage patterns and customers, and essentially be able to persuade them to perhaps reduce their consumption at particular times a day, that sort of thing. So there's a lot of opportunity out there. I don't think anyone's kind of really adopted it or quite figured all of it out right yet. But I'm going to jump into the live demo in just half a second. Hopefully things are still working. But one example we can look at is wholesale market compliance, right? So I work with one of our kind of larger utility customers, and they told me when generative AI came out there, they have a whole team of people that they get questions on regulatory compliance, and these analysts are very, very good at it. But there's a lot of manuals out there. There's a lot of documentation to kind of sift through, right? And oftentimes, on average, it takes one person one full day to answer a single question that they would get and are obligated to reply to research and correctly answer that question. With a grounded large language model using that RAG framework that I just described, you can do that in a matter of minutes or seconds now. And we can even show why it's accurate and where it got the information from. So we'll take a quick look at that. Yeah, let's just dive into the live demo, check out a few things real quick. And we've got about 15, 17 minutes left before we kind of do a little bit of Q&A. So I'll try to go as fast as I can while still touching upon some of the major stuff. Okay, so real quick, this is our platform. I'm not going to do too much of an H2O spiel right now, but I love it as a data scientist. It's part of the reason why I joined H2O. One of the cool things about this is we have the ability to spin up and down these kind of ephemeral compute instances to build models. We call them AI engines. You might be familiar with driverless AI. It's a really advanced AutoML tool that we'll look at right now. So I've got one of these running. Let's just take a quick look at it. A few motivational data sets we're going to look at, one of which is a pretty straightforward data set. Let's look at this one. It's not too big. I got a really small sample, 300,000 rows, 14 columns. We take a look at this. This is actually the data set from a Kaggle competition going on right now. Today is the last day of the competition. But if you haven't checked it out yet, you should definitely check it out. It's very relevant to the energy industry. The goal is to predict energy usage, but we've got both effectively demand and generation in there, right? So is consumption is a Boolean variable, which toggles between demand and consumption. Target is the actual energy usage there. And in this case, I think I limited it to about 10 households, right? But the competition, I think, has about 69. The point is there's a lot of fields in this data set, but pretty classic stuff. Weather data, temperature dew point, solar radiation, that sort of thing. And the goal is to really be able to predict the target, whether it be demand or generation, given a lot of information here. So I just wanted to show this data set. And when you click on it, it's really easy to build a model. Some of the concepts that are behind this is what I wanted to talk about really quickly. So let's say we want to predict that target. In driverless AI, the first thing we do is say, hey, driverless AI, I want to predict this thing. In this case, it's called target, but it could be anything. Therms, kWh, solar production, right? And we get a nice distribution of that variable, and it comes up with a plan of attack on the left. This plan of attack is dictated by 3 settings: accuracy, time, and interpretability. And this kind of just controls the scope of how hard we're going to work to solve this problem. In this case, a higher value of accuracy typically leads to a more accurate model, but there's some trade-offs there. Higher value of time gives it more time to reach a good solution. Again, there's trade-offs there. And interpretability kind of controls the search space. So if you turn interpretability all the way up to 10, you're going to be limited to the most interpretable models, like the linear regressions of the world. If you go all the way down to 1, any real model that you want to try is applicable, right? So in this case, maybe you want to use root mean squared error because it's a regression problem, MAPE, right, or symmetric MAPE. You can actually upload your own loss function. So if you have your own custom loss function or business KPI that you want to use, you can optimize against that. And so typically the first thing we want to do is tell it that, this is a forecasting problem, right? And so in that case, I might want to highlight the time column, say there's a date time, and now I'll say, okay, well, how far into the future do you want to go? Maybe we're doing like just a day ahead forecast, right? 24 hours. There's all sort of really advanced settings that, frankly, we don't have time to kind of go over. A whole series of expert settings that expert data scientists can go out there and, add their own models, tweak everything that happens behind the scenes. But generally speaking, even right now, you saw me click two things. I clicked predict this target, and here's a datetime column, and it's already learned a massive amount about it. What the frequency of the data is, how far in the future you really want to go, right? And at this point, I'll click launch in just a second. You could also create a leaderboard. So you could also, just to solve this problem, you could create a leaderboard that'll launch 10 to 12 different experiments of all different types, right? So I'm going to click launch just to kind of get that going, and we'll look at a completed one in just a second. And what's happening right now is it's going out there, it's checking the data, it's doing all sorts of data QA, QC. And then on the left, this should pop up in just a second. It's going to start iterating. And this is where the concept of feature evolution comes in. So what we do here is we use a genetic algorithm. We look at these 14 columns I provided, and we do automatic feature engineering. So we go out there and we say, what are all the possible ways to combine my features together and generate new features? And are they useful from a predictive standpoint, right? So, okay, that's taking probably a little bit too long. Let's just hop over to a completed one. Yeah, here we go. So this is kind of what it looks like when it's done. On the bottom left, we see the progression of that genetic algorithm, right? So this is the loss, in this case, mean absolute error. For what it's worth, I believe the current leaderboard for this competition, the winning solution right now has a 59 mean absolute error. Not at all apples to apples comparison. This is a sample data set. This is also the cross-validation loss function, so not a true out-of-sample prediction, but it's started to kind of be indicative of what you can get very quickly by clicking a button, right? It's like a baseline model. And I think the most important part is probably to focus on right here in the middle. These are all the features that got created, right? So if you hover over one of these, the top feature in this case is the lag of the target, which makes a lot of sense. So lags by 24 periods, but specifically grouped by a few other features that it found. Now, you or I might be domain experts. We might know the features that are really important that we should group by, but that's not always the case, right? And so the fact that you're able to go out there and figure out how to take these transformations of features automatically and learn as you go is really advanced. And this is where we see utilities starting to quickly go very fast in these process. Again, going from 9 months to a 2-week type of deal. There's just way too much in here to really cover because I do want to talk about generative AI in a second. But the last thing I want to show is, interpretability, right? So if we click on some of these models I've built, you can also quote unquote interpret them. So for any experiment you build, you can go out there and really get a full suite of analysis trying to understand what's going on. So one, I'm a forecasting nerd, so I always like to focus on this. Obviously, I focus on time series problems. And in this case, again, we've got what we call time group columns, but it's really the individual time series is split up by county, whether it's a business or not, and whether or not it's consumption or not. And it automatically figured out, by the way, I didn't tell it those three things is what separates the time series. It figured that out. And it's listing kind of the score, right, for each time series. It built a global model across all of that, and it's listing out the score for each one. But if you look here in the bottom left graphic, we can really zoom in and really understand very quickly how well it's performing. So green dots are the actuals, white is the forecast. And like I said, in this case, I quite literally clicked a button to get this far this quickly. I did this morning, my time, for what it's worth, building this model in just a few minutes. Right, so you can imagine if you get to this point in just a few minutes, imagine where you can go from there. Yeah, so I'm just going to flip over to generative AI because we are kind of running out of time a little bit. If we do have more time, I can definitely show the MLOps stuff as well. But let me just show a few examples of generative AI just so we have time to do that. I got to log back in. Yeah, so this is kind of our default. I call it the foundation of generative AI. So it's a RAG system, right? And so there's all sort of Python APIs that are built around this. So you as a data scientist, a developer can interact with all the really advanced models and features here. But just kind of walk you through how it works for, a typical workflow. we have a bunch of collections of data of documents, right? So we'll look at a few. I've created one for ISO New England. I took down all their market regulation manuals and ingested that. I have a few examples of utility bills, but just to show you how this would work, it's pretty straightforward. We would say my collection, everything I'm showing you with the UI, you can also do programmatically with code for what it's worth. But now we might want to add some documents. Let's see if I can find one really quickly on my computer. Yeah, I'll just take one of these as an example. I think it's a utility bill. And we would click upload and ingest that. So that might take a second, but really what's going on is that entire diagram I showed you with RAG. So we have been working on document AI for a long time, way before LLMs were a household name. And what we're able to do is really use really advanced OCR to extract text data, even if it's a very complex document with all sorts of infographics, tables, pictures, that sort of thing. We take it, we chunk it up, and we store it in a vector database, but you don't need to worry about any of that. You can tweak it if you want using the Python APIs, right? But typically you don't want to worry about that part. Typically you want to just say, here's my data. I want to start using it with generative AI. So like I said, that might take a second. There's a lot of other people kind of using the same thing I am. Let's just take a quick look at the market regulations one. So as you see here, I've created a collection with a series of PDFs. And for each PDF, we can just take a quick look. It's nothing crazy. It's public ISO New England manuals for market operations. Quite boring. Some heavy reading, right? So, but you can, going back to that use case, there's a lot of information here that if you're not an expert and you need to be able to answer questions, you need to be able to query this stuff very quickly, right? So let me kind of circle back and I'll go to market regulations, and you can start chatting with it. So if we kind of look through here, yeah, of course, we use generative AI to first look at what you gave us and say, hey, here's some example questions you might want to ask, right? So I'm just going to pick one. Oh, this is a good one. Let's see what this says. What's the purpose of the seasonally claimed nominated consumption limit? I actually don't know what that is. But as you go through here, we have really advanced settings. I'll talk through in just a second. The first thing we do is ask an LLM itself, right? So this is just like you going to ChatGPT, not looking at any data and just simply saying, what is the purpose of the seasonal claim nominated consumption limit? And it'll tell you something. And the thing with this stuff, as I'm sure everybody knows at this point, it's 100% confident in its response, even though it may or may not have any knowledge of what that is. But then when we apply kind of RAG, right? So if we look through here, we've flipped it around a little bit. The bottom one is LLM only, but this one is using RAG. So now we've actually looked at the data and tried to come up with an answer. And you can kind of see it is a much better answer. But most importantly, you can go back and understand exactly where it came from. Like, how did this model come up with this response? And we can go back and you can see here, these are the chunks that I was describing before. And you see a score at the bottom. That's cosine similarity. That's how similar the text chunks are given our query. And if we just kind of look at one of these, it's just going to highlight exactly, there we go. It went out there and figured out. I did not plan this, by the way. This is going much better than for a random kind of question I could have asked. This is a great example, right? It went out there and found exactly where it was defined in the documentation and sent that to the large language model to generate the response. So you're getting that sort of traceability and explainability back from these large language models, right? So that's just one really quick example. A few of the advanced settings just to kind of walk through. You may or may not be familiar with some of these things, but a system prompt. So basically you're saying, yeah, personality, but you're directing the large language model to focus in a particular way. So obviously we're using a system prompt here that says, you're effectively enterprise HOGBT created by H2O. We've seen this is fascinating. I'll give you a $200 tip if you answer the question correctly. We've seen, I think there's a recent paper that says if you do that, it actually improves performance quite a bit, which is quite frankly terrifying. But you can customize this. This is kind of just an example default we're using, right? But you can kind of customize the system prompt. You can pick which model you want to talk to. Even if you are using, if you're a Google shop or you're OpenAI, we can integrate with all those existing types of Gen AI technologies and integrate them here. So you can pick which model you want to use. And then I would say most importantly for the concepts I was describing before with RAG, there's options. So LLM only, no RAG, just talking to the model. It's going to make stuff up. It might get some stuff right, but it's going to make some stuff up. RAG is exactly what I already described, very straightforward. Hey, given these, similar chunks of data, what's your response? But there are, no free lunch. There are challenges with RAG as well. Sometimes cosine similarity doesn't find the most relevant chunks of text data, right? And so sometimes you might need to get a little creative. One approach to do that is hypothetical document embeddings. And what we do there is we say, it's kind of a two-staged approach. So first, we do LLM only. So we ask a question, and then we ask the model to spit something back. So exactly like this example here. And then we take both of those things and create an embedding and a retrieval vector. And we take both of those things, and then we do RAG. And the point of that is to really get at more of a semantic similarity, more relevant, right? So we want to see if the model can get us a little bit closer to a more relevant embedding when we go to look at our data, when we then go to look at the data, right? So that's where the hypothetical word comes from. And you can take that even a step further. So hide RAG plus is like yet another where you effectively, you do 3 calls to the LLM, right? So there's some pretty advanced settings. And then you can also customize kind of the RAG prompt before, the RAG prompt after. And maybe the last thing I'll quickly talk about here is self-reflection. So self-reflection, let's see if this works. Self-reflection is the ability for the model to kind of look at its own result and say, actually, let me make sure that was, let's go back to regular RAG too. Yep. Try to ask the question again, and with self-reflection, it can go out there and kind of ask itself, how good do you think you did? Yeah, how good do you think this result was, right? And try to come back with a little bit better of a response. So let's see what it comes back with. The other thing here is there's a lot of detailed information. If you have used ChatGPT, or if you've deployed generative AI on your own, you're probably aware calculating cost, and a lot of stuff is per token pricing, right, these days, and estimating for a given use case how many tokens you're going to use for API calls can be very challenging, right? So what we're able to do is kind of, with an entire RAG system, we can go out there and figure out exactly how much it would cost to really get every query done for you. So yeah, that's going to kind of continue for a little bit. I'm pretty much out of time. I just want to show one last very quick example of kind of extracting information. Same deal. We've got a single bill. So this is a public document. It's a bill, right? And so in a lot of countries, we don't have really advanced infrastructure for managing data. So metering data might not be accessible to the public, that sort of thing. And so sometimes we do want to do billing analysis where we actually go out there and say, I want to know what the total amount due is out of this. And now with like these RAG systems, see if I can go back to where I was. You can prompt your way there very quickly, right? So here's an example prompt I did right before I started talking this morning. I simply asked, what is the total amount due? If you ask an LLM, again, it's not looking at that bill, and it just comes up with 1, 2, 3, 4, 5, 6 as of March 31, 2022. Right. But if we actually look at the bill, and I'm not sure if this actually got it right, to be honest with you. Yeah, it looks like it did, 7482. So it was actually able to go out there and get the exact right information from the bill. But you can say things with, this will be the last thing I do. Yeah, let me just say, something like, please find the total amount due and return as a JSON with the following fields. Total amount, amount due. All right, and let's just see how that goes. Because the point here is if you're using APIs, using this kind of system as a framework, yeah, there you go. Now you can start extracting, every piece of information out of these bills and storing it as tabular data that can then be used with predictive models, with open source models, forecasting models, that sort of thing. All right, so I'm a little out of time there. I could talk for a long time about this, but let me go ahead and pause, and maybe we can move over to the Q&A portion.
Great, thanks very much, John. Yeah, please do put your questions in the chat, and we'll pick them up as we go. I guess one of the questions we often get with utilities and kind of energy consumers is around security and kind of like enterprise security and embedding, that kind of thing. How do you find the kind of other unique challenges that AI and generative AI poses, or do you think it's more just it's the same security challenges, just in a different context?
Yeah, I mean, that is like the penultimate kind of question, I think, for actually deploying this sort of thing. We've seen, and where we've focused, a lot of our customers are banks, right? So we also have the regulated utilities, but we also have a lot of banks, and banks are really, really regulated. There's huge financial penalties for getting things wrong, right? So in their case, AI governance is critical. So being able to deploy these sorts of things on premise, or even in air gap situations where they doesn't have access to the internet, all of that's really important. Content moderation, so defining and testing your guardrails that you put on top of what's coming out of these models. And then also, like, lots changed with Gen AI, but certain things haven't. The age-old adage of garbage in, garbage out still applies. So when you fine-tune a model or you are ingesting data, you first probably want to identify, is there toxic comments in the data? Is there PII in the data? And really doing a scan first to remove that sort of information, so the model, especially if you're fine-tuning, never learns that. Because once it learns that, it's virtually impossible to kind of get that knowledge out of it. So yeah, I don't know if that answers the question really well, but it's a big topic. It's a lot there. Yeah.
Another big topic kind of coming up in the chat is around copyrighted content and the kind of legal issues around that. What do you think the kind of, obviously it's hard to predict the legal outcomes of all of that, but what do you think the implications are for kind of energy sector organizations applying it?
Yeah, I mean, truthfully, very, very good question. Truthfully, I don't think we know the answer to that. I mean, I think there's a lot of cases being reviewed right now, but so far it's really been focused on, to my understanding, on image generation. So like Stable Diffusion, DALL-E, those types of models that, have been trained on images that may or may not belong to individual organization. But we haven't really got to the point yet where generative AI, in the case of large language models, has really seen that. There have been a few, right? So quick example, I think there was the famous one where like a lawyer was generating all of his briefs, right, using generative AI, and it was very obvious, and the court found it, and he basically lost his job, I believe. And there's also other situations where I think the car company Chevy was using generative AI, and they ended up like promoting Toyota on their website by accident, right? So those are those are the sorts of things that like will start to happen, and we will start to see legal ramifications. Final thought, my thinking is that if it's in the public domain, it's in the public domain. So if you have a large language model that's trained on open source data, it's open source data, and I think it's going to be a hard case to make the other way around. So
Yeah, definitely one that keeps the lawyers up at night. Another question from the chat, what was the best open LLM model that you found for energy questions? Have you found that some perform particularly better in some domains than others?
Yeah. Well, that's a very loaded question. I think what we're really finding is that like certain models perform very well at certain use cases. Something I don't really have a lot of time to go into is evaluation, right? So we have a framework we've built for evaluating not only large language models, but large language models plus RAG. And what we found, the key to evaluation, there's a lot of like public leaderboards out there that say Llama 2 70 billion is the best model at reasoning, for example, right? But these kind of generic benchmarks for reasoning, right? They're great, they're useful, but not necessarily what you want for a given use case. And what you need is like a benchmark for a given use case. So yeah, I guess sticking to the market regulation type of question where it's like, how well does this AI know the ISO market regulations? And that becomes the test that you need to evaluate all these models on. And what we've seen, just generally speaking, Llama 2 continues to be a very, very good model across the board in almost every use case we've found. Mixtral model that kind of came out, mixture of experts, is very good, very comparable results for its model size. Code Llama just came out, so there's a lot of use cases, which I'm kind of showing a little bit here on like using Assistant to generate code and that sort of thing, is a very good model. Yeah, and the last comment I would kind of make, I think the more important thing, we love to fall in love with our models, but the more important thing is to think about bigger picture items like context length. And I think now what we're really seeing is we've kind of maxed out a lot of the models on context length for open source models. And so more and more models are going to come out for long context. So we need to start evaluating those as well. Yeah.
In terms of applications for like network operators and that kind of stuff, are you aware of any AI applications in the UK that have been going on? I've got a few I can throw in answer to this question, but I don't know if you know of any.
Well, is it specifically applications of generative AI in the UK?
And more broadly, I guess, like AI, traditional machine learning.
Oh, well, there's like, yeah. Well, maybe not in the UK, so maybe I'll definitely lean on you for that. But just one sentence. Generally, yes. I mean, there's so much anomaly detection going on, that sort of thing. Fraud detection, bad actors, people like flipping their meters up and down. And again, just taking data out of bills and trying to have a large language model reason through, does this look rational, that sort of thing. But yeah, if you want, yeah, please go ahead from the UK.
So in UK, kind of DNO is doing like a lot of time series forecasting, some of which is old statistics models, some of which is new machine learning models. So kind of like forecasting individual substations. There's National Grid, electricity transmission doing the predictive maintenance, like detecting components on overhead lines type thing. So yeah, there's quite a broad range. There's also, plan optimization. How do we optimize the like outage plan, all of that kind of stuff. So yeah, quite a lot of different applications.
Fascinating. Yeah.
In terms of like getting started and what you need with this kind of platform, what state does the data need to be in to get decent results out of it? Do you need to have done a whole load of data cleaning and preparing and structuring in advance or not?
Well, the cool thing about generative AI is not so much anymore, because these large language models are kind of pre-trained. So I guess I think it's a dichotomous kind of question there. Number one, are you trying to fine tune a large language model on data? And in that case, yes, you very much need to be careful about, taking text data and, like I said, removing pieces of information that you don't want it to learn, right? So that part definitely hasn't changed. But again, I mean, what we've seen is that some of these like pre-trained foundational models, it's really hard to beat them by fine tuning, typically, in my experience. So oftentimes when we talk about data, it's really that part I was talking about on ingesting it into like a vector database and pairing that with with a model. And I just wanted to say, if you wanted to try out, we have a free version of kind of everything I just showed. And I'm just logging in real quick to, let's see if this will happen. But the reason why I'm showing this is from the RAG perspective, right? So if you want to understand, like, does my data facilitate the use case, you could go to our kind of free version here. And it is public, so obviously you probably want to be limited to public information that you upload here. But if you go to genai.ho.ai and you click on Enterprise HOGPT, you can do everything I was kind of demoing. You can start playing around and really understanding, does the data facilitate the use case that you're looking for? So Hopefully that answers the question.
Great. I think last question before we wrap up would be thinking about the skills and capabilities required in an organization to really make the most of this. So for an energy sector, like an energy supplier or a network, what kind of skills do you think they should be trying to develop and pursue? Is it the kind of deep data scientist? Is it like engineering? What do you think the important skills are?
I think that data science is not necessarily going away anytime soon, right? So a lot of folks are kind of saying like, well, it's just kind of eliminate the need for an analyst or a data scientist, right? And I don't necessarily agree. I think to answer the question, what we should be thinking about is just knowing the landscape, the current landscape of generative AI, and knowing where it's appropriate and where it's not. I think we're kind of in this like super hype cycle right now with generative AI, understandably so. But at some point in time, we're going to go back and we're really going to understand that it's the combination of generative AI and kind of like my whole talk was a little bit positioned as like generative AI plus traditional AI and predictive modeling. Those two things put together is really where I think we're going to start seeing the true gains. And like I said, on the predictive side, on the traditional side, you still need to have all the same sort of skills that we always needed to have in data scientists. That maybe one last comment. That being said, we will make it easier to democratize those sorts of technologies, though. Even this kind of really bad example I was kind of showing, I guess, with trying to prompt my way to a model, right? Let's see. I think I lost my tab here. But, just in words, I can say, like, when you're trying to prompt, like, create me a forecasting model, that kind of unlocks the ability to sort of do a lot more. Even if you don't know data science, you can start prompting a machine learning model to be trained on your data. So, yeah, hopefully that kind of answers the question.
Great. Thanks very much, John. For, I guess, those who are kind of in the energy space, one of the things that we've been doing recently is trying to look at, well, what challenges could AI be applied to? So with the AI for Decarbonisation Virtual Centre of Excellence, kind of releasing a challenge report and some decarbonisation challenge cards. So if you're excited about generative AI and traditional machine learning now, and you're going, where do I apply it? These are some of the challenges that we see in the sector that you can apply that to and help kind of accelerate decarbonisation. So have a look at those. And also, if you're kind of keen to get plugged into the sector more broadly and work out how do we innovate more effectively in the energy sector, we're hosting an Innovating to Net Zero conference in April. So it would be great to see you there. But thank you very much, John. Really interesting. Have a great afternoon, everybody.
Yeah, thanks. See you later.
Thank you.